Hi guys, the problem that we're going to be looking at today is going to involve uniform circular motion. So this concept is new to a lot of students, and so I'm going to spend a little bit of time here at the beginning just talking about some theory and some conceptual frameworks, and then we're going to move on to the example problem. So the basic question we want to start out with here is going to be if we have a particle, so let's draw this out here, some particle, and it is moving to the right with some velocity. So I'm also just going to say, let's say we have our coordinate system, x and y. We're not concerned with the position, but it's moving to the right. The question we want to ask is what acceleration can we apply to this particle so that it'll change direction? So up until now, we've been more concerned with sort of one-dimensional motion and maybe a little bit of projectile motion, but mostly we've been concerned with particles slowing down or speeding up. But we haven't been paying attention too much to the actual direction the particle is moving. And so now we want to ask, how can we actually change that direction? And so the answer to that would be, let's say that we apply an acceleration directly to the right, so an acceleration in the x direction. We know already that that's just going to work to speed up this velocity. So the magnitude will get bigger and bigger. And in the same way, if we apply an acceleration to the left, it'll slow down the velocity. So the magnitude will get smaller, but there will be no direction change. That's never going to work to change the direction of the velocity vector. It's not going to work to change the direction of the particle itself. So what we would need to do then is we need some component of our acceleration to be perpendicular to this velocity vector. And that'll be the part that is going to work to change the direction of the object. So let's say that we have, for instance, an acceleration pointing somewhere down and to the right. What we want to do conceptually is think of this as two separate accelerations. So we want to split this up into ax and ay. So it's just to say this acceleration vector we can say has a component in the x direction and it has a component in the y direction. And so then in terms of terminology, what we call ax is we call this the tangential acceleration. So ax is tangential, and then our ay is going to be our radial acceleration. So we're going to split up each acceleration to a tangential component and a radial component. And then now if we want to keep in mind what these do, the tangential component acts like a lot of things we've seen now before, which is just to say it will speed up or slow down the velocity. That's really all the tangential component is going to work to do. It's going to either make this velocity, the magnitude of this velocity bigger or smaller. The radial component is the one that's actually going to change the direction of this particle. So that actually might make it curve downward, for instance. And so the radial component is what we're going to be concerned with here. And so now for this video, we're going to be looking at what's called uniform circular motion. And so what that is whenever we have a particle that is going around in a circle, and uniform means it's going around with a constant velocity. So basically we'll have some particle and it's going to be going around in a circle. And so at all times, at all points on this circle, our velocity vector will be tangential. So it's basically traveling along in the circle for all times. So our next question is, of course, how do we get uniform circular motion? We know how we change our direction, but if we want this very special case where it's in this uniform circular motion, its velocity is constant, and it keeps moving in this constant circle, we can ask, what acceleration do we need in order to get this situation? And so again, we can see from here we know our tangential component of acceleration is what speeds up or slows this down. So in uniform circular motion, there is no speeding up or slowing down. So our tangential component of acceleration must be equal to 0, which is to say the component that is along the velocity vector must be 0. And so the only component we're left with in order to give us uniform circular motion is the radial component, and therefore that would be the component towards the center of this circle. So that's to say at each of these points, our acceleration vector must point towards the center of our circle. And so this is a very special condition, and that's one where at every point we somehow are applying this different acceleration. It's always going to be pointing in the direction of the center of the circle. But it turns out that we need the same magnitude acceleration at each of these points in order to keep it going around in a circle. And so then this is another thing that you should have learned from class, but the magnitude of this AR, which stands for A radial, the magnitude that we need in order to keep it going around in this special circular uniform motion is then equal to v squared over r. And I'm going to box this because this is very important. And so that's to say that the magnitude of the acceleration we need to be applying to this at every point needs to be pointing towards the middle, but the magnitude needs to be equal to whatever velocity it has as it's going around this, squared divided by the radius of the circle we want it to move in. So this is something we're going to use today. And again, keep in mind, this is a very special scenario. This is saying that we need to have exactly this magnitude of acceleration. Otherwise, we're going to have this won't be some constant radius circle, and everything will sort of be much more complicated. Okay, so let's look at the problem statement for today. And that says, how fast would a car have to round a turn with a radius of 75 meters in order for its acceleration to be numerically equal to g? Assume uniform circular motion. Okay, so we see that in this problem we have a case where they tell us there is uniform circular motion. So our first step here is let's draw the diagram. So I'm going to draw from the bird's eye view. I'll draw, this will be the car, and this is the bend that it wants to travel around. So its sort of motion will look something like this. So one thing we know is that for this to be uniform circular motion, the acceleration at every point on the car must be pointing towards the center of this circle. So we sort of want to imagine here, this bend will be maybe like a quarter of the full circle, and that circle will be sort of, we can extend it, will be something like this, and therefore this car will travel around that circle for at least some amount of time as it's going in the bend, and at each point in that motion, this acceleration must point towards the center of this circle that we've sort of pictured in our heads. And then the other thing we know is it says it's uniform, so that means that there is no tangential acceleration. The velocity is the same, and therefore we have our relation for uniform circular motion, which tells us that the magnitude of the radial acceleration, which is the only acceleration this car should be experiencing here, is v squared over r. So when it tells us that we want the acceleration on the car to be g, that's just telling us that our radial acceleration should be equal to g, which is 9.8 meters per second squared. It's just a number. And so basically we can plug in g should be equal to v squared over r, and then we can rearrange this and solve to get v should be square root of gr. And then you can plug that right into your calculator, and you should get a velocity of 27.1 meters per second. So what this tells us is that this car must have a velocity of 27.1 meters per second at each point in its motion in order to have an acceleration equal to 9.8 meters per second as it goes around this bend. And so again, this is uniform circular motion, so there's no speeding up, so this velocity should be constant throughout the curve. Okay, so let's review really quickly what we just did. For this problem, we first drew a diagram, and then we sort of noted that we were dealing with uniform circular motion. And so then that meant that we had a definite relation between acceleration, velocity, and radius. So we utilized our radial acceleration condition in order to solve for that velocity, given that we knew what we wanted our acceleration and what our radius should be. All right, I hope you guys learned a little something about uniform circular motion. So this is something that's going to come up a lot in dynamics. A lot of times the dynamics won't just be occurring along a line, but you might have some change in direction that you'll have to deal with. So knowing how these kinds of acceleration vectors split up is going to be very important. So if you have any comments about this video or any of these videos, please leave that on the comments survey, which is under the videos tab on TED. Thanks for watching.